Well, good afternoon, everyone. It's an honor and a pleasure to welcome Professor Hongjie Dai as the first Wynne Distinguished Lecturer of 2013. Professor Dai was born in Shaoyang, China, and he is currently the J.G. Jackson and C.J. Wood Professor of Chemistry at Stanford University. He's a leading figure and an authority on the basic science of carbon nanotubes and graphene and their application in nanoelectronics, nanomedicine, energy storage, and catalysis. Dr. Dai received a bachelor's degree in physics from Tsinghua University, Beijing in 1989, an MS in applied sciences from Columbia University in 1991, and a PhD in applied physics from Harvard University in 1994 under the direction of Professor Charles Lieber. After postdoctoral research at Harvard, he joined the Stanford faculty as an assistant professor in 1997. Among his many awards are an Alfred P. Sloan Research Fellowship, the American Chemical Society's ACS Award in Pure Chemistry, the Julius Springer Prize for Applied Physics, and the American Physical Society's James C. McGrody Prize for New Materials. He was elected to the American Academy of Arts and Sciences in 2009 and to the American Association for the Advancement of Science in 2011. Dr. Dai sits on the editorial boards of 8 journals, including Applied Physics, Advanced Functional Materials, Small, Nanoletters, and Nanotechnology. His past research is focused on novel carbon-based materials, but he has recently branched out to new hybrid materials, including nanocrystals and nanoparticles on graphene sheets. So please welcome Dr. Hongjie Dai and his talk entitled Novel Materials for Nanoscience and Nanotechnology. Dr. Dai.
Thank you. Thank you so much. Okay, thanks, Dr. Cardi, for this really wonderful introduction. I think you know me better than myself in some ways. Yeah, it's really a pleasure to be here today. It's an honor to be in this series, and I'd like to thank the invitation. And it's actually my first time in Canada, believe it or not. So I'm quite excited, and today I also spend time talking to a lot of young faculty here. I learn all the exciting things that they're doing. And it turns out we also have a lot of common interest. And hopefully you will see some of the data that I'll show today. Okay? So today I'd like to give you an overview of the work in my group. And it's not possible to talk about all the things we do. But I really want to talk about the things that at least I'm quite excited at the moment about what we do, okay? So I will cover quite a few areas, okay, which could be a little distracting to you if you feel it's not very focused. Okay, I will talk about 3 areas. One is in the area of nanobio, okay, using materials made in our group to do some biological applitions. So that's one major direction of the group. And these materials include carbon nanotubes and these metallic films. Okay, these are actually plasmonic films that's quite useful for doing biological detection. And then the second area is in the area of energy. So I'll mostly talk about growing materials on graphene and carbon nanotubes for the sake of energy storage or electrocatalysis. Okay, and I'll show you why we're doing this and what are the things that might be new out of this approach. And the other area my group works on is really to make materials with potentially very interesting physical properties that you can study, because I do have a physics background. So we're making materials that potentially have exotic physical effects, okay, either due to the size. In this particular case, we're making graphene nanoribbons, which has edges. which actually have interesting physics problems that you can study. But this part will be very, very brief. Okay, so let me get into the first topic quickly, which is to use nanomaterials for biology and medicine. And I really think that, I'm a person who really makes materials. Okay, so I really feel that if materials can be used for life science or medicine, that's definitely a very meaningful direction. So we would like to use the properties that you get out of these small size structures to do things that could improve life, okay? And so we hope we can do better imaging or detecting a protein that's related to a disease so that you can really help to maybe improve the diagnosis of diseases or even have better therapy for diseases like cancer and heart disease. And if you look around and see what are the major diseases out there, it turns out these are the 3 top killers of human beings. And the first one is actually heart disease. Okay, so a lot of people die of a heart attack. And the second one is cancer, okay? And the third one is actually a stroke, okay? So out of the 2, you actually have these, the number 1 killer is actually the vessel disease. Okay, so when you have your blood vessels clotted, then you have problem. Okay, you could have a heart attack if the clot is in the heart, or you could have a stroke if the clot is in the brain. Okay, so being able to image detect these diseases, cancer included, if you can detect the cancer in the early stages, you could also save lives. Okay, so if any of your material made in the lab that can be useful, potentially useful for doing all of this, even if you do this for mice, okay, try to understand the disease better, I think that's a very meaningful direction. Okay, so let me talk about carbon nanotubes. Okay, so they are, one-dimensional systems, and they have this kind of band structure, which is a characteristic to 1D systems. What that means is that you have these Van Hove singularities, and you can have optical transitions between these levels, very like in molecules. And then you can also have light that's being emitted from these systems. So in this case, you excite between these higher energy spacing, and then they emit at smaller energies. So you can actually get absorption in the visible, okay, or something like 800 nanometer. And then they emit light in the IR almost. Okay, they emit like 1 micron to 1.4 micron. And we call this region the near IR2 window, okay? Because traditionally near IR is about 800 nanometers, okay? This is still near IR, but it's in a slightly different window. So now you have these fluorophores really. They emit light, they fluoresce at long wavelength. So what can you do with it? Right, they're fluorescent. And so if you look at the absorbance of biological tissues or things like blood, okay, skin, fat, you see there's a window here between about 700 to 1.4 micron. The absorbance is small, okay? And that's the so-called optical window for biological imaging, because light is not absorbed a lot, okay? So that's a very good thing for penetrating into the body to do optical imaging. And so we call this near IR1, which is about 800 to 900 nanometers. And then this longer wavelength, we call it near IR2 because it's a different window. Now these nanotubes are emitting or fluorescent in the long wavelength window. And why is that window useful? And that's simply because of scattering is reduced at longer wavelength. Okay, so imagine you have light coming from inside of the body, coming out to the outside for detection and imaging. If the light is scattered less, that means they're going to mostly straight out, right? Then your imaging will give you higher resolution, spatial resolution. Otherwise, your image will be smeared. Okay, I'll show you some data. So this is a very simple physics. Rayleigh scattering, for example, scales with lambda to the -4. Okay, so the longer is the wavelength, the less is the scattering for Rayleigh scattering, and the same thing for biological tissues. So what that means is that you can actually get higher resolution of imaging inside the body, okay, if you can detect fluorescence at longer wavelength, okay. And why haven't people done this before? One of the reasons is not many molecules fluoresce, okay, at such long wavelengths. Very few. I'll show you a few more examples. And the other reason is convenience, okay. People are equipped with silicon cameras, okay. I have one here, and you have your silicon cameras too, right? But I bet you don't have an in-gas detector on you, right? So this is a very special detector. It's a semiconductor with a smaller band gap that's sensitive to longer wavelengths of light. Okay, so this is a special detector, and it's a hassle to use it, and so not many people actually do this kind of detection. So for a long time, nobody really cared about this region, even though they know the absorbance is still okay, it's low, you can still use it, but not really many people realize that this part is actually quite important if you do want to do good imaging. So carbon nanotube, as I said, is one of the things that emit in this window, and then there are also quantum dots, okay. Lead sulfide, silver sulfide, these things emit at about 1200 nanometer, or you can tune them by composition or size. And then there are organic molecules as well that can emit at such a wavelength, and this is one example, and I'll show you another example later. Okay, so in order to make these things useful for biological imaging, you have to make them water soluble. Okay, so in this case, I'm showing you one way we can coat these nanotubes with this surfactant molecule so that they are hydrophilic. Okay, they can go into water. You see, this is really a nice solution of these nanotubes. So once they're coated like this, they are water soluble. They can be injected into the blood, and they're not toxic. Okay, so we do this with a lot of mice, and all the mice are actually very safe, as long as you do this very careful hydrophilic coating of the nanotubes. So now we can really use them for imaging in the body. And let me show you a piece of data in a beaker first. Okay, so you can put these nanotubes at the bottom of a beaker and fill it with fat tissue or some sort of mimic of fat, like that. Okay, and you can see that they become, you cannot image them well if the fat is too thick. Okay, and that's because of scattering. Right, so light comes out from the bottom of the beaker, and they have to go through all these fatty molecules, and they're scattered, and therefore the image becomes smeared. Okay, but you see the smearing is not as bad as ICG, which is a molecule that emits at 800 nanometer, and that's the traditional near IR. Okay, so you see that at shorter wavelength, which is 800 nanometer, the smearing is much, much worse, so that this object no longer look like a line, right? Because of scattering. So that right away tells you that you will be able to image things at higher resolution if you detect things at longer wavelength. So in 2009, we actually did this experiment for the first time. Right? So People do fluorescence imaging of mice a lot, but previously only below 900. Okay, so this is the first time we did it with nanotubes. So this was, to the right was a mouse with no nanotube in the body. And you see it's totally dark because the body does not emit these near IR2 light due to autofluorescence. Autofluorescence is very low. So when we inject this much of a nanotube into the mouse vessel, you can start to see that the vessels are lighting up. Okay, so these are vessels definitely in the body underneath the skin, and later in 2011, we did the imaging of the inside of the body. Okay, so we inject the nanotubes inside the body and follow where they go. Okay, so in the first few seconds, they go to the lungs to get oxygen. Okay, and then as the time goes by, they go to the kidney and they light up the kidney, and then they go to the liver, spleen. Okay, so now these are the organs that's really in the body. Okay, so this gives you some sense that you can actually penetrate into the body and image what's inside. Okay, it's non-invasive way to look at what's going on in there. So images like this give you a sense that the body is actually somewhat transparent because of this reduced scattering. And we also did this analysis called principal component analysis, PCA, which basically groups the similar pixels together into different, into the same color. So you can really resolve every organ really well, major organ in the body, by simple imaging like this. Okay, and most recently, we really started to try to use this technique to see whether we can image important features, okay, in the body, such as the blood vessels, okay, as I mentioned in the beginning. So this disease is called peripheral artery disease. Okay, so this is a vessel disease where the clot is actually in the leg of a patient. Okay, this is actually a fairly common disease as well. And so you would like to be able to image where the blockage is, okay? And you would also like to measure the flow velocity of the blood, okay? So people do this in the clinic all the time, and they have to use a combination of techniques like CT, ultrasound, or laser Doppler to get this information, okay? So we are working with a doctor in the medical school. They have a mouse model. Okay, so here's the leg of a mouse, and that's opened up, which is invasive. Right? We don't want to do that. We want to do a non-invasive imaging of these blood vessels and see if they're clotted or blocked anywhere, and be able to measure flows of blood. Okay, so the way we do that is we take these carbon nanotubes and we attach a fluorophore to them. So we attach an 800 nanometer dye, IR dye, 800 to the tube. So now you have two wavelengths of light coming out of this complex. And then we use a silicon camera and the InGas camera to measure both, to detect both wavelengths and get two images and compare them side by side. So this image is taking, this is a mouse. Okay, so a mouse is lying here, and these are the two legs and tail. So you see, after we injected these complex in there and detected the shorter wavelength dye, 800 nanometer, you see it's pretty fuzzy. Okay, you know there's light coming out, you know there are some big vessels in there, but you really don't see very much detail. And now you switch to this InGas detector and measure longer wavelengths of light, and that's what you see. Okay, so now you see the image is much more clear, right? And you can see the vessels very well, okay? And the smallest vessel we can see from these profiles is about 30 microns, okay? And these vessels are about 1 millimeter deep, 1 to 3 millimeter deep from the skin. Okay, so this is now a big difference in terms of what you can do with optical imaging, okay, of animal models. Okay, now you can actually really see these vessels quite well and see their structure and utilize this reduced scattering effects, okay, to better resolve things in a body. And ideally, you know, the optical imaging is limited by the diffraction limit, okay, about half of the wavelength of light, okay. So that would be the most ideal case, but in this case, you still have some scattering, which is still causing this broadening effect, but at least we're now doing much better than before. So here's a side-by-side comparison, which can give you a sense of what the difference is. Okay, the difference is quite obvious to me, and an analogy I want to bring up is this kind of phenomena that you actually see in real life. So this was a recent image from Beijing. They had a huge smog recently, and it's the same place being photographed. And in one case, you have a lot of smog. Okay, so these are basically particles. So particles would scatter light, and you don't really see anything. You cannot resolve any feature because of the scattering. So if it's a clear day like this, it's much different in terms of imaging quality. We can also do imaging like this in real time. Okay, so this is something that's better than things like MRI, because MRI is not able to take images in real time. So this is pretty much like taking videos, okay, using your iPhone. So in this case, we inject the blood into a healthy mouse, and you watch how the blood flows, okay? So you see the mouse is healthy, so the blood vessels are very open, and blood flows quickly, and it light up the leg quickly. And you can actually measure the time course. Okay, so these are at different time points. It's getting brighter and brighter, and you can actually extract the blood flow based on this data. And the last image here is this PCA again, this principal component analysis. And in this case, we found interesting, you see two colors, two components. So one of them is actually artery, and the other one is a vein. Okay, so in other words, even though they are too close together to be resolved very well from this kind of image, but because of the different dynamics of blood flow in these two type of vessels, you can actually find out actually there's a vein next to an artery, okay, by doing this analysis. So the flow velocity you can measure is about 5 centimeters per second. And then you can do the same thing with other mice and really look at a lot of vessels. In this case, here's a mouse that we can see there are a lot of vessels, and we can tell which ones are the artery and which ones are the vein. And we can even see some of the heart, part of the heart. Okay, so the heart is deep in the body. We can see that. We can see the aorta, which provides oxygenated blood to the body. Okay, and then we can do this with mice with disease. Okay, so the vessels are now clotted. So you can see the vessel here does not light up as quickly. And then eventually, the blood slowly flows through the leg. Okay, so the rate of blood flow is much slower than in the previous case. And you can measure the flow velocity very well by simply following the flow front, okay? Right? So the rest of the mouse is already lighting up, but then this vessel is not, and gradually light up due to the that's very slow blood flow. So in this case, the flow velocity is about 0.16 centimeter per second, which is very slow. Okay, and the speed here is actually too slow to be detected by ultrasound. Okay, that's what our collaborator told us. Anyway, so this is the imaging story I want to tell you. Simply utilizing these long wavelength emissions, you can actually do imaging much better in mice to see some of the processes and understand some of the. Actually, right now we're looking at the regrowth of vessels. You can actually look at damage the vessel, how it regrows in real space and time. Okay, so that's quite interesting. So these are the features of this technique. We call it near IR2 imaging. You have high resolution, millimeters deep capability, and you can do this at video rate for blood flow measurements. And to make this a general imaging approach, I think we need a few things together. Okay, the first one is actually we need more molecules or agents that emit light in this wavelength. And quantum dots is one of them. And this is actually a mouse with a tumor at the leg that accumulate the quantum dots, and we can do this kind of imaging. The emission is about 1,200 nanometers. And the other type of molecule is a real molecule. It's a small organic molecule like this. Okay, the emission is about 1050. Okay, that's why it's called IR 1050. And but the problem for chemists in the audience, that the problem with molecules like this is they don't dissolve in water. Okay, so they are really not designed for biological imaging. They're actually designed for making infrared lasers. Okay, so lately we've been trying to trap these dyes into like proteins, like a BSA molecule, and that made them soluble. Okay, now you can use the complex here for imaging. So we need molecules that's really safe and biocompatible, so that potentially can really go into the clinic for imaging of humans. And the other thing is that on the detector side, we could improve the capability of these cameras. And I was talking to Professor Bond today, and he seemed to have a way to replace the InGas detector with a silicon detector by an up conversion mechanism. I think that could be very, very powerful for this technique as well. Okay, so detector and fluorophores. Okay, so that's the first story, and I'll move on to these films I mentioned in the beginning for microarrays. Okay, this is really a project we hope to develop to detect or diagnose diseases better. Now, I don't know if you're familiar with microarrays, but the idea here is quite simple. You put different capture molecules on a substrate, which is commonly glass. Okay, so you put these baits on the surface, and then you capture the molecules in a serum or in urine samples from patients. And then you tag these captured molecules with a secondary antibody with a fluorophore. Okay, and then you detect the fluorescence of each spot, and then you can tell how many molecules are being captured on each spot. Okay, so it's a way to detect a lot of molecules on one slide. Okay, so very fast because you're putting different baits on them, so you can really fish out a lot of molecules to detect. So you use very little amount of sample. So this potentially is a tool that can really make detection much better in the clinic. Okay, but the trouble has been the sensitivity is always limited. Okay, you really cannot detect a lot of the molecules at the concentrations relevant in the clinic. Okay. So we recently found a very simple way to very efficiently enhance this sensitivity. The way we do that is to use these gold films that's made on glass. Okay, so these are very small islands of gold that's grown on a piece of glass. We found that this is a very good substrate for making these arrays. And the reason is because of plasmonic enhancement of fluorescence. Okay, so in other words, these metal structures actually are plasmonic, which is these collective oscillations of electrons in the metal structure, and they can couple to the fluorophore and enhance fluorescence. Okay. So the way we make these films is very simple. It's very much like what do you do to make to develop photographs in the old days. Okay, probably a lot of young students don't know what I'm talking about. But we used to go to the darkroom and put these films into a solution, shake them, and you develop these black and white photographs. So what you're doing is really to put silver particles on that paper to get a picture. So here you're doing very much like that, but you're growing a gold film on the glass, right? So a slide goes in and you pull it out, you make this gold film. And these gold films, as you notice, they are not continuous. They are irregular. They're not even controlled in any way, but we can make them very quickly, very cheaply. Okay. So what's good about them, as I mentioned, is that if you put a fluorophore on the slide, the fluorescence can be enhanced. Okay. Now, a lot of you, if you work with fluorescence, you know that metals would typically quench fluorescence. Okay. So this is why people rarely use a metal film for protein arrays or peptide arrays. Okay, because you don't get any fluorescence out, so you lose any detection sensitivity. But in these films, we found you can actually enhance the fluorescence of this IR dye I mentioned earlier for imaging by up to 100 times. Okay, so it's a very large enhancement of fluorescence. And so the mechanism of this fluorescence I mentioned is plasmonic enhancement. And so what we did was to vary the film structure. Okay, so you can actually make the size of these particles to be different. So over here it becomes continuous, okay, film. And so what we found that these two type of films in the middle actually can enhance fluorescence, but these guys here actually have some quenching effect. Okay, so what's going on is that to enhance fluorescence, you want to have two factors being enhanced. One is the electric field. Okay, so if you have a lot of small gaps between particles, your field gets enhanced, and that enhances your excitation of these fluorophores. So you get a E squared term there for the fluorescence enhancement. And the second requirement we found is that the size of these particles, even though they're irregular, but when they are on the order of about 200 nanometer or so, like these two, okay, they enhance fluorescence. Okay, and the reason is that you actually get enhanced radiative decay. Okay, so the excited states of the fluorophore can be emitting light more efficiently, therefore enhance the quantum yield, and therefore giving it a brighter signal. So this is the absorbance of the film, of these two films. And you see there's this peak here. Okay, that's the plasmonic excitation in the film. And when the absorbance matches the emission of the fluorophore, and that's when these fluorescence are enhanced the most. Okay, so once you reach these requirements, you can get up to 100 times fluorescence enhancement, which now you can use to do protein detection. And for chemists in the room, you know that on gold, the thiochemistry that's very well developed. So you can use it to coat the surface with all kinds of molecules to make it a very good for capturing molecules for detection. And you can also block the non-specific binding very well using these kind of polyethylene glycol hydrophilic chains. Okay, so the chemistry here is quite easy to develop on gold. It's actually easier than on glass. So let me just show you a few examples of using them for detecting molecules. So in this case, we're capturing a cancer a biomarker, okay, CEA. And we want to see what concentrations of CEA we can detect by doing this on the gold, right? Because we can enhance the fluorescence. And so it turns out we can get down to femtomolar sensitivity. So this is a concentration, you know, from nanomolar to femtomolar. You can see we get a linear detection all the way to femtomolar. And on glass, the signal is much weaker. This is log scale. So much weaker signal, and you lose sensitivity below about 1 picomolar. Okay, this is very, very reproducible. And you look at the images, you can tell right away this is much brighter on gold than on glass. Okay, so you have a very high enhancement of the signal. And the other important piece of this is actually really the chemistry, because if you think about it, your enhancement of fluorescence is really to boost that positive signal. But the surface chemistry of blocking non-specific effects is what's giving you this low signal down here. Okay, so being able to do chemistry well on the surface is going to be important to getting this very broad dynamic range. Okay, so it's both physics and chemistry that's going to make this to work. Physical enhancement and chemical blocking. And here's another example. We are detecting antibodies this is actually in a human serum. So we have all these autoantibodies in people with diseases like rheumatoid arthritis or lupus. And we're detecting these antibodies on gold and glass. You see on glass, at the same intensity scale, you see very little signal, so the signal here is very low. And then there are other kinds of substrate like the nitrocellulose paper, which has a lot of pores, so you can get a lot of things to be captured, but then at the same time, you also have very high background. Okay, so your dynamic range here is very limited in both cases, but on the gold substrate, you really boost both the signal and minimize the non-specific signal. Okay, so I think this is a technique now that can really make the array to detect molecules at very low concentrations, okay, which I think will be relevant for diagnostics. Okay. Another example has to do with cytokines, and cytokines are molecules that often comes up in the body if you have an inflammation of some sort, including cancer, which is a huge inflammation. So you can see that, again, on gold, we have a lot of signal, very low background, and on glass, the signal is 2 orders of magnitude lower, and sensitivity is lower. Nitrocellulose, the background is very high. Okay, so this is really working, and we use this to measure what cancer cells secrete in a solution, in a cell culture. So we can actually measure 3 types of cytokine very well for these ovarian cancer cells. And if you do this with nitrocellulose, I think you can probably tell these 2 types are there, they're above the background, but then the 3rd type is really mixed with the background. Okay, it's not, you won't be able to say this is really there. Okay, so I think it's really quite promising in terms of doing protein detection. So this is the end of the second story, which is a simple approach to measure molecules at high concentration with very high throughput. Okay. So I think it could be useful for proteomics and the diagnostics, and there are companies now that start to pay attention to this, and they may want to use it for things like diabetes diagnosis, for instance. So we're beginning to work with them. Okay, so now I want to move to the last part of the talk, which has to do with graphene. We got into graphene actually because of these ribbons, okay? And they look very similar to a tube. If you open up a tube, it's a ribbon, but they have these edges, okay? So these edges are what's interesting in terms of physics, okay? A lot of theory, what the edges can do. And this is the famous example. And if you calculate the electronic property of such a ribbon, the edge here actually can give you localized states, okay? So states can be localized at these edges, and they can also be spin polarized, okay, which is very, very exotic. In other words, the spin of the states on one side of the edge is gonna be spin up, okay, and on the other side, the spins will be going down, okay, and it's antiferromagnetically coupled. And you can use electric fields to manipulate these edges so that it's all spin down, okay? So it becomes a spin filter, right? So only this spin can pass. So this got a lot of interest many years ago now, but even to this day, this was not seen experimentally, okay? Because we don't really know how to make such a ribbon with such perfection, okay? So that's what got us interested in the beginning. So in 2008, my group made some ribbons, okay? And these are shown here. And you know, it's a very simple process, but over the years, we really try to improve the synthesis, and including this way of opening up a nanotube. Okay, so a group like Rice, Jim Tool, and us did the same thing pretty much. Open up nanotubes to make ribbons, and it does work. Right, so the way we did it at the time was we coat a tube with a polymer photoresist, and then you peel it off from the substrate, then the side of the tube that's touching the substrate is not coated by the polymer. So you can just do a plasma etching, okay, so that this row of atoms is removed, okay. So this works really well and gave us some ribbons. Lately, we've been trying even simpler methods like sonication, okay. You can sonicate nanotubes, and sometimes you actually get ribbons, okay. So it's a very simple process, but there are some details you have to control. And we do things like high-resolution imaging, and we look at how good the edges are, whether these are potentially good for things predicted by theory. So in this case, you see that the edges are pretty good. Okay, I don't think it's atomically smooth, but very smooth. Okay, and we collaborated with a physics group at Berkeley, Mike Cromie's group. And they did STM imaging of these ribbons. And this is the edge of the ribbon, and you see it's quite smooth. And as they scan from the edge to the middle, you can see that this peak here is decreasing, is disappearing as you go from here to the middle. So they interpret that as these edge states, okay, that people have predicted. So that was a pretty exciting time. So maybe these ribbons can be used to study phenomena like that. But we're still trying to improve this kind of making process. Can we really make something that's atomically well-defined and controlled? And my own group did some electrical measurements all the way down to about 2 Kelvin and of an individual ribbon. And we can see single electron charging Coulomb blockade. And we can look at some of these excited states. So these parallel lines are these excited states along the, confined by the length of the ribbon. So all this stuff, okay? And the data here basically shows the ribbon quality is pretty good. And you see that low temperature, the conductance goes down to very low, okay? And that's simply because it's actually a semiconductor, okay? With a band gap of about 50 electron volts. So when you cool them down, they have this huge modulation of the conductance. Anyway, so the last part has to do with using these carbon materials for energy research, okay? And the contribution I think my group made, I'm not really an energy expert, okay? I'm just a materials scientist. So we make materials that I think is actually interesting in terms of doing energy research. And the idea we have is this covalent coupling between carbon and inorganic materials, okay? I'll tell you what I mean by that. And so basically we can make a variety of inorganic nanoparticles on carbon and bond the two together very strongly, okay, potentially with covalent carbon to metal bonding as a material for doing energy storage or catalysis, okay? And I'll show you some advantages, and I'll tell you the reason we started this work. A long time ago, actually, we were doing a lot of electronic device work. And for example, we have a graphene here, and we try to put a dielectric material on top so that we can put on gates and do electrical measurements. But what we found is that these films, let's say the dielectric film here, aluminum oxide, it doesn't really like to grow on the substrate, on the graphene, because graphene is such an inert structure. But they go to the edges. Okay, so that means the edges are actually chemically reactive, and you can grow stuff from these defect sites. Okay, and this suggested that if you want to grow things on such a substrate, you actually need defects. Okay, so that's something we've been doing. So we make a lot of defects in graphene. So these are graphene oxide or graphite oxide. So we oxidize them with acid so that you have all these functional groups. Okay, oxygen, OH, or carboxyl groups. And then we grow these particles on top of them. Okay, so the way that works is actually we have a nucleation and growth process. So these metal ions would bond with this negative charged oxygen, okay, and stick. So that's the first step. It's a nucleation step. And then you can control the conditions so that the nucleation sites grow a particle for you. So this way you actually have very strong bonding between the particle and the carbon. So we call it a strongly coupled hybrid. And we believe it's actually useful for energy storage or catalysis because this is our strongly coupled system versus this more traditional way which you make your particle. Okay, a lot of people would make a battery material, for example, and then mix them with carbon, right? So you need a carbon anyway. But in our case, ours is right on top of a sheet. And the electron transport between the particle and the sheet is very easy. So you get electrons in and out very quickly. So you can charge and discharge very quickly, because that's really the idea. And it turns out to work quite well. Okay. And another aspect of this is that the particles grown on a sheet of graphene, they actually give you different morphology than the same growth in the solution. Okay, so the substrate actually provides a template that actually can give you a different morphology or shape of the particle, which is also quite interesting. So let me show you a few examples. One of them is cobalt oxide, okay, particles grown on graphene. And another one is nickel hydroxide, okay, which is a battery material. We can grow them on graphene as well. So it's stacked on the sheet. And another example is moly disulfide, which is a semiconductor and a catalyst. So these are sheet-like structure as well, and they are on top of these graphene, okay? And this turns out to be a catalyst for hydrogen evolution reaction, HER. And the reason it worked very well, we think, is actually because of these edges. Look at a lot of edges in these sheets, and they are not these three-dimensional particles. We can make nanorods. Okay, these are lithium manganese iron phosphate nanorods on graphene. And if you don't grow them on graphene, they would make a lot of huge particles, okay, which would give you less good performance. So I'm sure you know a lot about battery. A lot of work, excellent work is done here in Linda Nazar's group, for example, and a lot of other groups. So we have supercapacitors, lithium-ion battery, but you would like to make things better, right? So for example, can you make batteries that's much faster, so you can charge and discharge very quickly? Or can you have batteries that have much higher energy density than lithium ions, okay? So this example here is these nanorods I mentioned grown on graphene. Because they're so small rods, okay, and ions can go along the radius direction of the rods. So, and the electrons transport is very fast because it's right on top of a conductor. And we found that they can be, they work very quickly. Okay, in this case, the discharging here, okay, you can do at very high rate. Okay, so we went all the way to 100 C, and this material can be discharged very quickly. And so, for example, in this 20 C case, which takes 73 minutes to discharge, the capacity is still above 100, okay, milliamp hour per gram. It's a very fast discharge process, and the stability is pretty good. Okay. Another example has to do with these nickel hydroxide plates. Okay, and nickel hydroxide is very insulating. Okay, it's very, very insulating. So normally its charge or discharge is very slow. Okay, so we found that if you grow them on graphene, it's actually a very quick. The charge and discharge can be very quick, and it's actually useful for making faster batteries. Okay, so everybody knows here Thomas Edison, who invented the light bulb, but he also invented the batteries. Okay, the battery he invented was a nickel ion. Okay, so one side is nickel, one side is iron, and you have potassium hydroxide as the electrolyte, and you can basically oxidize nickel or reduce nickel, and then oxidize iron or reduce iron, and then make a battery. So it's been used for more than 100 years. It's good. It's a battery, so the energy density is good. It's safe. Okay, it uses water and KOH as electrolyte, but the charge and discharge has been very slow. Okay. So here's a photo of him holding his battery more than 100 years ago. So we made this battery by changing the electrode, right? So we made a nickel, in this case, on carbon nanotube, okay? And we made iron on graphene, okay? And both of them can be charged and discharged quickly. Now we put them together and see how they perform. Right, so that's the discharge curve, and you see the voltage is about 1 volt because this is in aqueous solution. But you see the charge and discharge here is very fast. I mean, we can do this very quickly in a matter of minutes or seconds. 2-minute charge or 10 seconds discharge. Okay, so this is really a battery. It's not supercapacitor. It's redox battery. So the energy density is actually higher than supercaps, but the speed is actually similar to supercaps. Okay, so we call it an ultra-fast battery. It really is much faster than the battery Edison invented many years ago. And the reporters actually, after they saw the paper, they dig out some history. And they actually found this photo, which is a car that's a EV made 100 years ago. Okay, and the battery in this EV is the nickel iron battery. But now I think maybe we could improve it, okay, by being able to recharge it in a matter of minutes, okay, over a cup of coffee, rather than staying in a motel and wait for your car to recharge. Okay, so this I think is an interesting way to speed up batteries. All right, so I think almost done, but there's one more thing I want to say, which has to do with catalysis, and there are these very fundamental reactions, such as reducing, evolving hydrogen from water, right? So it's water splitting, or the reverse reaction, okay, hydrogen oxidation, and oxygen reduction, or water splitting to give you oxygen. So these are really, really important and fundamental reactions that have barriers, okay, kinetic barriers that's very difficult to overcome, and you normally don't get much current even if you are above the thermodynamic limit of the voltage. So you need catalysts. Okay, a lot of precious metal are being used as a catalyst, as a lot of you know. So you would like to have non-precious metal catalysts. And we found that this material, cobalt oxide on graphene, is actually a very good catalyst for oxygen reduction in alkaline solutions. Later, we made it on carbon nanotubes, and turns out to be even better, okay? Because nanotubes are better conductors. And you have the interior of the tube that's actually not damaged. So they can actually conduct electrons even better than the graphene that's damaged on the sheets, okay? So it's actually bifunctional as well. We can get ORR and OER with the same catalyst, okay? And the performance is pretty good. What I want to mention is really when we grow them on the sheets, okay, so this is current of oxygen reduction, it's really much better than when you grow them and mix with carbon. Okay, this is true for a lot of materials, okay. So we really think that strong coupling there is helping. And in basic solutions, this material actually can be better than platinum. Okay, we get higher current than platinum. in basic solutions. Okay. Now, what evidence do I have that is strong coupling? Well, we did some X-ray absorption measurements, and this is the carbon signal. And I want to just point out in the middle here, these carbons are the carbon that's bonded to oxygen. In other words, these are oxidized carbon. And you see after you grow a nanoparticle on top, the most change we see in the spectrum is that peak. Okay, so that means that's really where this nucleation happens. Okay, these oxygen groups are grabbing the metal, and the result of that is some sort of charge redistribution, which changes that intensity. Okay, so this is a spectroscopy. This is actually done right here in Canada in the light source. I have a collaborator in the CLS. Okay, so one application of this is actually to use it for metal air battery. I talked to Professor Chen today, who is an expert on this. We're using it for zinc air battery, okay, which have high energy density than lithium ion. Okay, so lithium ion energy density is 160, and zinc air is 350. Okay, so very good energy density. Your cell phone would last much longer, or your car would drive much longer before you have to recharge. And the basic reaction here is really zinc is oxidized on one side, and oxygen is reduced on the other side. Okay, so you want a good oxygen reduction catalyst. So again, it's very safe. Zinc is safe, not non-toxic, high energy. And but to make it rechargeable, though, you have to be able to also go to the other direction, which is oxygen evolution. Okay, so you really need both OR and OER to be really good in order to have good performance. So we're using two materials for the battery right now. One is the cobalt, as I mentioned, for oxygen reduction. And this is a piece of new data that is still being reviewed. It's a nickel ion layered double hydroxide. Okay, it's a very thin plates that's made on nanotubes. And this turns out to be the best OER catalyst that we can make. Anyway, and then we combine these two for the zinc air battery, and this is the primary battery. So you're basically oxidizing zinc all the way until all the zinc is used up. Okay, so it's got a very good energy density. And then we can also make it rechargeable. So we can oxidize the zinc, okay, for 10 hours. So your battery would run for 10 hours, and then you charge it for 10 hours. What that does is that they put the zinc ions back onto the electrode. So it's zinc dissolving and being plated back and forth. So that's a battery, okay? And the thing to note is this potential difference here. The smaller, the better, okay? Because that means your overpotential would be the smallest. So this overpotential we're getting here is actually one of the smallest reported in literature because of the activity of the catalyst. Okay, even though there is still a 0.8 volts difference, but that's the best we can do for now. Anyway, so that's the end of the talk, and so the basic projects in my group is really to make materials and study the properties and then figure out what they might be useful for. And I really like these biological directions because I think it can really make a difference. And it's important to actually mention that there is a very big gap between physical scientists and medical scientists, and that's how I feel. They don't know what we can do, and we don't know what they need. Okay, so at Stanford, the good thing is about the medical school is right across the street, so we can do all of this. If we don't have a medical school, it's going to be really hard for us to do the stuff I told you today. Okay, so and then at the end, I'd like to thank all the people who made contribution to these projects in including Shirley Tan here, who actually started these protein detection in the group using a very different approach, but eventually evolved into what I told you today. That's being, that I think is really working quite well. And then a lot of people and collaborators. And thank you very much.